All right, so today, our last day of Calculus 1, we want to review what we've done and preview again Calculus 2 and Multivariable Calculus. I want to sort of focus on what calculus is all about today, you might say. And not showing you a ton of details of things by hand, but instead showing you some things on Mathematica that I got here. So I got a few different sections here. And by the way, I'll share this Mathematica notebook with you after class. And you can feel free to play with it, so to speak, if you want. I've got these different sections. This one is just a general question, what is calculus? And then we'll get a little bit more specific and say, where have we been in Calculus 1? What is Calculus 2 about? And how about, say, multivariable calculus and differential equations? So what is calculus overall? What have we been learning about this entire semester, big picture-wise? To applied mathematicians, statisticians, scientists, and I should say, and engineers, go ahead and add that here. Calculus is about methods, you might say, to model quantities that are related to each other, like distance is related to time, velocity is related to time, population is related to time. Maybe you've got two cars that are going toward each other, their positions are related to each other over time. Y depends on X along some curve, lots of relationships. And we want to model those relationships and make predictions about what can happen over time. Like I said, I've got a lot of different Mathematica code in here, some of it off of something called the Wolfram Demonstrations Project, which is a place you can go to download lots of different things that people have done around the world to show you how math interacts with different things in science and engineering, for example. You've got these different topics you can browse, you can download different kinds of code, and you can run the code. And this particular code that I have right here, it's called a predator-prey ecosystem, real-time agent-based simulation. It's one of my favorites. It's fairly simple and it's the way it looks, but it's kind of fun to watch. What does this represent? Well, the purple dots represent rabbits, and the orange dots represent foxes. And this is going to be a simulation of the foxes running around, chasing the rabbits, and effectively trying to eat them. We can run the simulation, and we watch the orange dots chase the purple dots around. Again, the purple dots are the rabbits, the orange dots are the foxes, and you see the purple dots kind of disappearing to some degree because the foxes are eating them. And well, it's pretty interesting because if you think about watching this over time, it's kind of hard to predict what's going to happen. You can change various parameters. We can reset it. We can, for example, change the mobility of the foxes or the mobility of the rabbits. Let's make the rabbits be able to move faster, and maybe the growth rate of the foxes, make that high as well, and we can see what happens. We can see if that affects things. Run the simulation again. Again, it seems hard to predict here what's going to happen, but I am seeing it looks like the foxes are kind of taken over. They're the orange dots, but maybe not. The rabbits start to escape them, and it's almost like they're going around and around now to some degree. Does this really happen in the real world? You'd have to actually try to look at real world data to see if this happens. But if nothing else, it's kind of fun to think about, fun to watch, to see what happens over time. You can make lots of interesting things happen. And again, I'll share this notebook with you after class today, and you can certainly feel free to run these things. This code runs what's called a continuous predator-prey model, like rabbits and foxes say, whereas the previous one was discrete with a temporal component, meaning, with a spatial component, meaning the foxes and rabbits could move around. This particular model doesn't have a spatial component. We only are concerned with the populations. These axes represent the populations of the rabbits and the foxes. Well, the vertical axis is the population, rabbits in red, foxes in blue, and the horizontal axis is time. And what we're seeing here is periodic behavior in a rabbit-fox model. The populations go up and down over time. You can actually put these together in a parametric curve and see how rabbit and fox populations change over time this way. The curve goes around and around and around, meaning the rabbit and fox population, which are these axes here, change over time. And I can also change the initial populations by moving this spot right here to say way out there. And I can see what happens now. It's a bit more interesting. It's still a periodic kind of behavior. The rabbit and fox populations vary in a periodic way and come back to where they start. But it's kind of interesting because they get real close to zero for a while. They almost both die off before all of a sudden the rabbit population gets really high. The curve moves over here to the right before the fox population starts to catch back up again because now they have lots of food. Again, does this really happen in the real world? Probably not exactly this way. It's unlikely that your rabbit and fox populations will be exactly periodic. But it's an interesting thing to think about and maybe compare with reality, compare with experiment. I also have some animations that I make with, for example, this balloon from the movie Up, showing you up-down motion over time. Is this really graphing the velocity versus time? Actually, no. This is graphing the position versus time. I purposely made it wrong. This one, I believe, is graphing the velocity versus time. So the position, the red graph down there is not giving you the height. It's giving you velocity. It's positive when the balloon goes up and negative when the balloon goes down. And again, you can play around with this and see what you have. So that's how scientists, engineers, business people, economists, etc., how they view calculus. How about pure mathematicians who like mathematicians for its own sake, mathematics for its own sake? That, by the way, is I think the best definition of pure mathematician. They like math just for its own sake. They may not care about whether it has applications or not. Am I a pure mathematician? Well, I do like pure math, but I also like applications. I do enjoy the fact that it's got applications. To pure mathematicians, calculus actually gets a new name. It's called analysis. And we have a class here called real analysis, which is about delving into the foundations of calculus, trying to prove things like, say, the fundamental theorem of calculus using deductive logic. It actually takes quite a bit of work to do that. It actually is not easy at all. It's a very advanced class. But pure mathematicians wonder about pure mathematical facts, like how do you factor a humongous integer like this? Well, Mathematica can do it. There's the output. What is this output telling you? It's actually telling you that this number, this huge number, is really 2 to the 5th times 3 to the 1st times 5 to the 1st times 323,339 to the 1st. Why did I pick that number? Well, that turns out to be a prime factor. That's a prime factor, and here's another prime factor. If you now go ahead and multiply these things, you get back the number you started with. You can plug in a random number into Mathematica and ask whether it's prime or not. Prime Q will return true if this is prime, and false if it's not prime. It says true, it is prime. And you can compute or reduce fractions, for example. You can try to ask and perhaps answer abstract kinds of questions. For example, are there infinitely many primes? If you make a table here, the primes do seem to go on and on for a long time, at least. For example, 37 is prime. I can keep going down this table. I see 127 is prime. I made this go up to 200, and I did get even 199 being prime. If you make as big a table as you want, say going out to 10,000 places, 10,000 whole numbers, you will keep seeing primes every so often, although they get kind of more spaced out. So you might wonder, do the primes ever end? The answer is no, there are actually infinitely many primes. However, and that's actually fairly easy to prove, there are also things called twin primes, which are 2 apart, like 5 and 7 are 2 apart, and 11 and 13 are 2 apart, 17 and 19 are 2 apart. Those are called twin primes. You might wonder whether there are infinitely many pairs of twin primes that are just 2 units apart. And the answer is that nobody knows. Nobody has ever figured out how to prove that there are infinitely many pairs of twin primes. And also, nobody has disproved it. That's an open question in math. Math actually has a lot of questions that nobody has ever figured out the answer to. And that's what pure mathematicians do as research, is they try to figure out answers to those questions. Are there numbers that are not rational? How can we be sure they exist? Have you heard of irrational numbers? Like square root of 2? What's the decimal expansion of square root of 2? Well, there's the first 100 digits. How about the first 1,000 digits? I can run an animation to see the first 1,000 digits of the square root of 2. And just like pi, these digits seem to go on and on forever and ever without a repeating pattern. But wait a minute, who would ever take the time to write out an infinite decimal expansion and check that when you square it, you get 2? Who would ever do such a thing? Certainly I would never do such a thing. And in fact, if you think about it, there can't be a single person in the history of the world who's ever taken all the digits of square root of 2, written them out, and squared it, and saw that, hey, it does equal 2. So that actually does bring up a pure mathematical question. How can you be sure that irrational numbers like square root of 2 exist? It actually takes proof, and the proof does not involve looking at infinitely many digits, though you can prove that these things have infinitely many digits that don't have a repeating pattern. It's hard work. It's all related to the nature of infinity. Have you ever heard that 0.9 repeating equals 1? Some people are shaking or nodding their head yes, a few people I see. It actually does. 0.9 repeating actually does equal 1. What? How can that possibly be? Well, certainly if you represent 0.99 repeating as an infinite sum, which you can do, this particular summation here represents 9/10 plus 9/100 plus 9,000 plus 9/10,000 plus 900,000 plus 9 millionths, etc. That's what 0.9 repeating really represents. And if you have Mathematica computed, it says the answer is 1. Is Mathematica lying? No, it is telling you the truth. 0.9 repeating does equal 1. Here's my favorite little proof of that. If 0.9 repeating doesn't equal 1, okay, tell me what's between them. You can't think of anything, so they must be equal. Is that really a proof? Well, okay. I claim you can't think of anything between them. My son said, well, why don't I just add a 5 at the end? Is that your question? Except you can't do such a thing, which is related to adding a 5 at the end. You can't, if the decimal expansion goes on forever, you can't say, oh, put a number at the end. That's the key. So you can't say it's 0.9 repeating forever and then at the very end put a 5, because the 0.9s go on forever. There's nothing, they never stop. You can't put something at the end. Question?
0.9 repeating goes to infinity, could also be equal to infinity.
No, because it is a decimal. It does represent this summation, which never does get above 1.
So would 0.9 repeating over 0.9 repeating equal 1?
Yeah, the ratio of a number to itself would equal 1. Yeah, and 0.9 repeating itself does equal 1.
So is infinity over infinity 1?
No, infinity over infinity is indeterminate, and you'd have to compute what it equals in a limit based on L'Hopital's rule, like we talked about. How should limits be defined? Why is this necessary? We talked about this example before. This limit is 1/6. However, if you try zooming in toward the vertical axis here, all of a sudden, the computer seems to say the limit doesn't exist. You get something crazy like this. What is that? What's going on there? That's actually numerical error. And the existence of numerical error like this tells you you need to really understand limits well if you're going to avoid realizing that this is numerical error, if you're going to be able to tell. However, in some cases, it's actually not numerical error. If you graph sine of 1 over x and approach the origin, the graph here also gets wilder and wilder looking. However, this is not numerical error. The graph actually looks like that. It actually oscillates infinitely often near 0. So that's an example that shows you that weird things can happen. These limits don't necessarily exist. I look at this pure math and say, hey, I think this is pretty neat, pretty beautiful. Maybe it's got applications, maybe it doesn't, but it's neat to think about. And I worship God because of that, that he's given us the minds to understand it, and then also that he has structured the universe in a mathematical way that can be understood. We can think of these things as worthy of praise. Where have we been in Calculus 1? At the very beginning of the course, we reviewed elementary functions, which are functions that are most useful. Those include power functions, polynomial functions, rational functions, and their inverses. And code like this will show you how to think about an inverse as a reflection across the line y equals x. That red graph is y equals x squared. And the ending graph right here, kind of purplish, is y equals square root of x. And these are inverse functions when you restrict the domain to being all non-negative numbers. We also thought about exponential functions and their inverses, logarithms. Here's another example showing you how to find the graph of the logarithm by reflecting the graph of an exponential across the line y equals x. So it's like, once again, kind of a fun thing to think about, how to get one graph from the other. We talked about that early in the semester. Trig functions and their inverses, you can play with these things if you like. That was the foundation, that was chapter 1, reviewing precalculus, all these useful functions. At the very end of chapter 1, we got into the theory of limits based on an intuitive approach with graphs and numerical values. We did talk a little bit about epsilons and deltas and those windows where the graph exited, but that wasn't a big focus for us. That is a focus more for a class like real analysis. We did some algebraic approaches where we factored and canceled. And ultimately, we also used algebraic properties like the limit of a sum, limit of f of x plus g of x as x approaches some number a is equal to the limit of the first function as x approaches a plus the limit of the second function as x approaches a, assuming these limits exist. Okay, I'm not going to enter this because I haven't defined f and g here, but that was a very useful property for us in also proving things about derivatives. Derivatives being the next topic, they are based on limits. There's the definition of the derivative as the limit of a difference quotient. So for example, if I think about f of x equals x squared, I can try to compute the limit of a difference quotient, f of x plus h minus f of x all divided by h as h goes to 0. Mathematica will go ahead and compute this and give me 2x, which is of course the same as the derivative of x squared. Okay, so derivatives are based on limits. In fact, everything in calculus is based on limits, including those infinite decimals. They're really infinite sums, but how do you add infinitely many things? You have to rigorously define it using the idea of a limit. We approximated derivatives from data. We did that a little bit. We did graphical and numerical interpretations of derivatives, including units where appropriate. If you have the graph of the sine function, well, its derivative is the cosine function, and you should be able to understand that graphically if you plot both the sine function and the cosine function over an interval like 0 to 2 pi. It should make intuitive sense when you think about the slopes. The derivative of the blue graph here is the yellowish graph. In other words, the outputs of the yellowish graph give you the slopes of the blue graph. At x equals 0, for example, the output of the yellowish graph is about 1. That means the slope of the blue graph is 1. As x gets bigger and approaches pi over 2, we see the yellow graph go down towards 0. So the slope of the blue graph is going towards 0. When x is bigger than pi over 2, and here, now the yellow graph is negative, so the slope of the blue graph must be negative. And it's most negative in slope when x equals pi. There are relationships between these graphs that you can understand if you think about slopes, and also can ultimately help you do your analysis and your modeling. Symbolic rules like linearity, product rule, quotient rule, chain rule are fundamental to the course. And when you really think about these things, they're pretty amazing. If you got a function like, say, sine of x cubed times e to the 2x, all divided by the log of cosine of tangent of x, that's a pretty crazy function. I have no idea what its graph looks like. I'm pretty interested. We'll look at it here in a second. Isn't it amazing that we could apply the quotient rule and the product rule and the chain rule to find the derivative of this thing? And of course, Mathematica can do it as well. And we could combine these things, we could simplify. Well, Mathematica is having a hard time simplifying it, it looks like. Maybe, oh, there it did it. Isn't that amazing? That's astonishing. When you really think about that, right? That you could, and if I made that a gateway problem, in theory, If you practice enough, you could get that answer. You don't make any mistakes. That's astonishing that these derivative rules could help us do such a crazy thing. And yeah, I'm kind of interested in knowing what the plot of this looks like now. I have no idea. How crazy is it? I don't know. This is going to probably have some vertical asymptotes, but let's just see what it looks like. Okay, so it's pretty crazy looking. Looks like infinitely many oscillations in here. Less crazy when x is negative. We only let x go to, say, 1 here or something. Okay, yeah, pretty crazy. Evidently, the original function is the blue graph, and its derivative is the yellowish graph. But it's hard to tell exactly what's going on, especially when you get these big oscillations in here, okay? But amazingly, we can calculate the derivative like this. That's a pretty amazing thing. We did some special situations with implicit differentiation, and well, actually, we didn't do logarithmic differentiation in our class, though I did it in the lectures from fall 2019. We did a little bit of theory, mean value theorem most prominently, related to the increasing and decreasing function theorem. And if you did the reading at the end of chapter 3, you also learned about the constant function theorem and the racetrack principle. I didn't have time to talk about those in here. That's some theory that can help you do applications like graph sketching and optimization. Maximizing and minimizing functions is kind of the main application that we do in Calculus 1, as well as related rates. Then we just touch on integrals. We do briefly talk about the definition of an integral as a limit of what are called Riemann sums, which really are adding up areas of rectangles like we talked about. We can approximate integrals with data, like with a right-hand sum. We can interpret integrals used as areas under graphs, and we can talk about their properties, like the integral of a sum is the sum of the integrals. That's linearity. And most prominently, the fundamental theorem of calculus. Okay? Mostly we focused on how to understand them, how to use them. We didn't really focus on the proofs. To fully do proofs of these things, that would be a real analysis topic. And we talked about applications like finding distance traveled by integrating the speed and finding displacement by integrating the velocity, for example. And we also talked about probability. If you end up taking Calculus 2, how would I summarize the topics in Calculus 2? Well, first thing we do in Calculus 2 is we do review integrals, like we've been doing here at the end. And then we come to a point where we realize doing integrals, computing integrals, really is harder than doing derivatives. In other words, finding antiderivatives is definitely harder than derivatives. There are some certain ones to memorize, like the integral of 1 over 1 plus x squared is one actually worth memorizing. It's inverse tangent or arctangent of x plus c. Now, Mathematica doesn't do plus c, but when you do this kind of integral, you should put the plus c. The authors of Mathematica say they assume you know to put the plus c. You know, if you didn't know the derivative of arctangent was 1 over 1 plus x squared, you'd look at that integral and you'd say, I have no idea what to do. But that is something that's worth memorizing. We also introduce some techniques for integration, most prominently something called integration by substitution and integration by parts. Integration by substitution helps you integrate things like, x squared times cosine of x cubed. The reason this is doable, a similar problem came up on your exam on Wednesday. The reason it's doable, it turns out, is because the thing that's out here is almost the derivative of the thing in here, right? The x cubed, its derivative would be 3x squared. If I had a 3 here, it would be the derivative of the inside, but I don't. However, the fact that it's almost the derivative of x cubed means this integral is possible to do. And the answer is going to be, if I can do it in my head here, I think 1/3 sine of x cubed plus c. Again, Mathematica doesn't put the plus c, but you would want to do that. Okay, that comes from my experience in doing those integrals. But this method that you'll learn in Calc 2 would help you do it. Something called integration by parts helps you do integrals, things like this. X times e to the negative 3x is an example of something best done by a technique called integration by parts, not substitution. This thing here is not the derivative or close to the derivative of this thing. Integration by parts, which I'm not explaining, helps you compute this integral. It turns out you get that. And again, you would want to add a plus c. Expand it there. However, sometimes integrals are just too hard to do by hand. Maybe because they are very, very complicated. Like, say, integrating, I don't know, how about x squared minus x minus 6 over maybe x cubed minus x. Doing that kind of integral is possible, but it's pretty hard. There's the answer. Log means natural log, and you'd want to, again, put a plus c at the end. You have to use either Mathematica, maybe a table, or something called partial fractions, which is another technique that I do mention here. Trigonometric substitutions and identities also turn out to be useful. And these integrals are all useful in engineering and science. In particular, I'm thinking of something called Fourier series. Fourier series and Fourier transforms as being subjects in advanced science and engineering to which integrals are very handy to do. And Fourier series and Fourier transforms are really important in science and engineering, for one thing, because they help you, they're part of the modern communication scheme. They help you with, you might call it signal processing. For example, television signals or radio signals or cell phone signals. That's all based on, how do those signals carry information? It's all related to these things called Fourier series and Fourier transforms, which are based on knowing how to do integrals. Some integrals are just too hard. And in fact, to do them, you have to come up with a new name for a new kind of function. Integrating sine of x squared involves a new function called Fresnel s, which stands for the Fresnel sine function. Integrating cosine of x squared introduces a new function called Fresnel c. Integrating e to the negative x squared turns out to be important in many applications in probability and statistics because it's related to something called the normal distribution. This introduces a new function called ERF, which stands for error function. What are these things? They're just functions you've never heard of before. That's all they are. They can be defined using integrals. But how do you compute these functions without a computer? You'd have to do what's called numerical integration, which we touched on a little bit. Looks like I did not put numerical integration in here. Maybe I should. Numerical integration involves doing summations like left-hand sums and right-hand sums and fancier things. The fanciest thing that you typically talk about in calculus 2 is something called Simpson's rule. To try to approximate areas when the fundamental theorem of calculus, while true, is not of much help, perhaps because you've got one of these non-elementary functions, Fresnel s, Fresnel c, ERF, that you've never heard of before, and you're trying to approximate it. If you don't have something like Mathematica, you'd have to do some sort of summation to approximate the appropriate area under the graph. Applications of integrals include continuing applications to physics and motion, except we do try to go higher dimensional. We've talked about two-dimensional motion in here with parametric curves. You can generalize that to three-dimensional motion. You can talk about parametric curves in space, and the ideas of velocity vectors, for example, still carry over, and the integral of the velocity is still the change in position. To represent those changes, you need to talk about vectors. Still can say the fluid flow rate can be integrated to get the change in volume. We talked about that here in Calc 1. Geometry, you can find areas, you can find volumes. You can prove the volume of a sphere is what is it? 4/3 pi r cubed? Actually, I'm forgetting it. Does that sound right? Or is that the surface area? 4/3 pi r cubed. I'm forgetting the volume of a sphere. Does that sound right to people? Yeah. Okay, 4/3 pi r cubed is the volume of a sphere. You can derive that using integrals. It was discovered back a couple thousand years ago by Archimedes, although he didn't use our notation, didn't use our formulas. But you can derive that kind of formula with calculus very easily. Maybe I shouldn't say very easily. Applications to probability and statistics still, more physics, density, mass, center of mass, work done by a force. Chain lifting problems, what's that about? Well, that's like if you are lifting something with a chain, you might wonder how much work do I have to do against gravity? And that's a calculus problem if the chain has a decent amount of mass to it. Pumping problems means pumping water out of a tank, for example. How much work do you have to do? Economics, actuarial applications. Numerical sequences and series, which is related to infinite sums. Lots of weird things can happen with these series that you would never expect. This is intriguing to a mathematician, for example. If you add up the numbers 1/k squared as k goes from 1 to infinity, if you do this infinite sum, amazingly, the answer involves pi. It's pi squared over 6. And you look at that and you're like, what? How can that answer involve pi? Where are the circles? Actually, there's a 3 blue, 1 brown video where he explains this intuitively. It's worth watching if you're interested in knowing why such an infinite sum would involve pi. It's actually a very famous problem. The first person to figure it out was named Euler, and he became very famous in part because of that. Lots of weird things. If you you can do something similar, you can go k goes from 1 to infinity, 1 over, say, k to the 10th power. That also involves pi. The answer is pi to the 10th over 93,555. What? If you do odd powers of k, though, all of a sudden Mathematica says, well, the answer is not a simple thing in terms of pi. It's zeta of 3. What's that? That's called the Riemann zeta function. You can approximate it. It's about 1.20206. Who would care about such a thing? Lots of people, actually, including you, should care about the zeta function. Let me tell you a little bit about it. It's related to something called the Riemann hypothesis, which is the most famous unsolved problem in math. If you can prove the Riemann hypothesis, which to this date nobody has done, you will win $1 million, become world famous for as long as we're in the world here, okay? Riemann hypothesis is the most famous unsolved problem in math. What does it say? It's about the Riemann zeta function. What? What does it say? It says the real part of every non-trivial zero of the Riemann zeta function is 1/2. What? What? That's the most famous problem in math? Are you kidding me? What? What in the world is this about? Who would care about such a thing? It turns out you should care, because if the Riemann hypothesis is true, it turns out that that makes many cryptosystems relatively safe, at least until we develop more powerful quantum computers. And that makes your transactions on the internet safe. Because this turns out to be related to the distribution of prime numbers. It's definitely not clear how. And prime numbers are key to cryptosystems online, and probably cryptocurrencies too, if you're interested in that. So the Riemann hypothesis, whether it's true or false, will affect your life. It seems to be true. Nobody's ever disproved it, and numerical evidence seems to indicate that it's true. So it seems like we can trust it as being the foundation for our cryptosystems. But nobody knows for sure if it's true. If you prove it's true, or if you prove it's false, you'll win that $1 million and become world famous. Of course, it's pretty difficult because nobody's ever done it so far. There are all sorts of other things, power series, Taylor series, Fourier series, like I mentioned before. Oh, I have to show you one thing kind of fun here. I'm going to make a manipulate. This is a pretty cool thing here of a plot. And what am I going to plot? Well, one thing I'm going to plot is the cosine function. And another thing I'm going to plot is a certain weird looking summation. Let's see, I'm going to let k go from 1 to n here. And how should I do this here? I'm going to go -1 to the k plus 1 over, again, this is weird, 2k minus, I need to think here, -1. Think about this here. I want to do a factorial. Oh no, I think maybe I just want two. Maybe the parenthesis k minus 1 should be in parentheses. 2 times k minus 1 factorial. You know the exclamation point in math means factorial. 5 factorial means 5 times 4 times 3 times 2 times 1. And then I think I want a x to the 2k minus 1 here. What in the world am I doing here? Hang on here. Hopefully I haven't made a mistake. Let's graph this from -6 pi to 6 pi. Make the plot range -2 to 2. And let's let n increase, starting at 1 and going up to 10 in increments of 1. Or let's go up to 20. What in the world am I going to see here? Hopefully, if I haven't made a mistake, we'll see something kind of cool. That blue graph is the cosine graph. What is the yellowish graph? It's the summation for different values of n. First n is 1. Here's n is 2. Here's n is 4. And if you, or 3, excuse me, and if you play this, isn't that pretty? The yellow graph gets closer and closer to the blue graph. What in the world's going on here? This is an example of something called a Taylor polynomial that is converging to the Taylor series of the cosine function as n increases. Let's go faster here. And that makes the graph of the yellow function get closer and closer to the blue graph as n increases. And it's almost like it's flapping its wings. Maybe if I let this increase by 2 instead of 1 each time, it'll look more like wing flapping. No, okay. Less like wing flapping, actually. In the infinite sum, it actually equals the cosine function, which this animation should make not too surprising. It doesn't look like as much like wing flapping as I thought it was going to, but that's okay. That's pretty astonishing. And it turns out to be useful, including to differential equations, which is another subject that we talk about in Calc 2. Solving differential equations with special methods like separation of variables, analyzing them with things called slope fields, and approximating solutions with something called Euler's method, different models of growth and decay, interacting species like that rabbit and fox model I was talking about earlier, physics models like a mass and a spring, are all applications of differential equations, which we talk about to some extent in Calculus 2. What comes after Calculus 2? Calculus 3? Well, some people call it that. What is Calculus 3? You can also call it multivariable calculus. How about Calculus 4? Many people call that differential equations. It's an entire course by itself. We've talked a little bit about multivariable calculus in here. Made some kind of fun graphs of multivariable calculus functions here. That's the graph of cosine of x times sine of y. Very pretty kind of graph there. What does its contour map look like? It looks pretty as well. There's its contour map. If you combine cosines and sines in these kinds of ways, you can get some pretty interesting multivariable calculus kinds of graphs. You can also animate this graph as one of the parameters, either x or y, changes. I'm graphing this as a function of x as y changes. What do I get? I get what's called a standing wave. You can model standing waves in physics. You can also model things called traveling waves. You can get a traveling wave moving to the right like this. You know, you could pretend that's a rope and you got two people at either end of the rope moving it up and down as it goes here. That one's traveling to the right. With a little modification, you can make it travel to the left as time goes by, or at least in this case, as y changes. Y could represent time. You could graph this in higher dimensions. There's what it looks like in higher dimensions. The contour plot is maybe not as interesting this time, though still somewhat interesting. Stripes. You can graph parametric curves in 3 dimensions. Here's a 3-dimensional parametric curve. It's a spiral, and you can graph, like you see there, a position vector and a velocity vector. I can stop this and look at it. Move this around. I see it spiraling upward as time goes by. So you can model 3-dimensional motion that way. Another interesting topic is something called the curvature of a curve. And that red circle that you see is called the osculating circle of the curve. It best approximates the blue curve. The yellowish graph is measuring how curved the blue curve is. It's the curvature of the blue curve. Also is related to the size of the osculating circle. When the yellow graph is high, the red circle is small. When the yellow graph is low, the red circle is big. This is useful, for example, in designing roller coasters. You'd want to think about osculating circles when you design roller coasters because that would affect the physics of the forces you would feel, for example. You can combine multivariable calculus and differential equations to, for example, make animations of like mini solar systems here. Fun, fun, fun. This mini solar system does satisfy Kepler's laws, if you've ever heard of that. Planets that are closer to the sun don't take as long to go around the sun. They also go on elliptical orbits with the sun at a focus of the ellipse. And there's something relating these ellipse sizes to the period of motion, which I won't get into. You can make these pictures 3-dimensional if you like to see the solar system. You can also make these accurate. I mean, this is a little toy solar system. That's not the actual solar system. That's not actually our sun, and those are not actually planets there. But if you use appropriate units and use the right scale, you can actually make a model of our solar system. Though it's more informative if you say just do the inner solar system instead of the entire thing because the scale gets strange. So that is my summary of what we've done. You know, what is calculus about overall? Where have we been in Calculus 1? What is Calc 2 about? And what are some of the basics of what multivariable calculus and differential equations are about? A lot of the things we do in Calculus 1, you might say are not so necessary in lower dimensions. For example, optimization, you know, those optimization problems that we did where we took the derivative, set it equal to 0 to find the critical points, and then used like the first derivative test or the second derivative test to decide on maxes and mins. You could talk about all that without talking about calculus because you could just make your graphs on your calculator and say, hey, calculator, where's the low point? Where's the high point? What's the max or min? However, when you go to higher dimensional problems, calculator is not much help anymore. Can't visualize it. The dimension's too high. It might be a 10-dimensional problem or something. But there are still methods that generalize what we do in Calc 1 that can still allow you to program a computer to solve for a max or min, for example, in a 10-dimensional space. Maybe a function that's got 10 variables as input and 1 variable as output. There are algorithms, even though you can't visualize them, that generalize what we do here that can help you test for maxes and mins, for example. That's where the theory really pays off. That's pretty advanced. Okay. So thanks for being in the class. I wish you a good finals week ahead, and I'm praying for you. And Maybe I'll see you around next year. Okay? Have a good day and a good week.